topic of this lecture is data and learning. My name is Johan Hagelbäck and I'm a senior lecturer in computer science at Linnaeus University. First we're going to talk about data and data representation. Data consists of inputs and outputs. Each set of inputs and outputs is an independent example, or sometimes called instance, of a data. It could be one image of a cat, a set of test results for a patient with diabetes, and so on. The inputs consist of one or more, often quite many, values called attributes or features. Output consists of one or more values called classes or categories. The attributes are variables describing an example of a data. They can be of different types, numbers, integers or floats, or they can be nominal or categorical, which is a finite set of discrete categories. For example, a car, a boat, a plane, the digit 2, the letter A, and so on. When we work with machine learning, we usually encounter a couple of common data sets. And the hello world problem of machine learning is what we often call the iris dataset. In this dataset, we learn to distinguish between 3 subspecies of the iris flower based on measurements on the flowers. So we have 3 categories: the iris versicolor, iris setosa, and iris virginica, and we have 4 numerical attributes, which are measurements on the leaves in the flowers. And the dataset consists of 150 examples, 50 of each category, so it's a balanced dataset. So parts of the dataset looks like this. We have measurements for sepal length and ridge, petal length and ridge, and they map to one of the 3 categories: setosa, versicolor, and virginica. A dataset we often call the hello world problem of image recognition is the MNIST dataset. It's a dataset containing images of handwritten digits, so lots of people have written digits 0 to 9 and we have scanned and digitalized them. The dataset has a training set of 60,000 examples and a test set of 10,000 examples. And there are, of course, 10 categories, 0 to 9. And each image is 28 times 28 pixels in grayscale. So it looks like this. We have the actual handwritten digits, and they map to a 2-dimensional array of values. So each of these images can be seen as 28 times 28 matrix of float values. Each value represents the darkness of the pixels, so 0 is white, the background, and 1 is black, the central parts of the written digits. And sometimes the dataset has values, integer values between 0 and 255 instead. To use the dataset, we need to flatten the input array to a 28 times 28 input vector with then 784 values. So all these 784 values are the inputs, and they are mapped to one output value, the actual digit 0 to 9. So quite lots of input values compared to the iris dataset, where we only had 4 attributes. And MNIST is what we call an image recognition problem. A much more complex image recognition problem is Cypher 10. It consists of 60,000 images, 50,000 for training, 10,000 for testing, of size 32 times 32 pixels. It has 10 categories: airplane, automobile, bird, and so on. And the input vector must then be flattened to 32 times 32 pixels times 3 color channels, because we have the RGB color channels. So in this case we have 32 times 32 times 3, which equals 3072 input values, so quite many input values. And some parts of the dataset looks like this. So we have the airplane and some pictures of planes, and we have automobile, bird, cat, deer, etc. So 10 categories of different types of objects that we shall recognize. An even more complex dataset is the ImageNet challenge, and this challenge is an annual contest for image recognition. And the training dataset consists of 1.2 million images and 1,000 possible categories. The validation set for the challenge with test set is a random subset of 50,000 images. Images can differ in size, but in average resolution is 482 times 415 pixels. And there's two tasks, machine learning tasks here. Recognition, what's in an image? Is it a cat? Is it a dog? Etc. And image localization, where an object is in the picture, as can be seen in the picture in the lower right corner. So it has detected person, a dog, and a chair, and also where in the picture these objects are. We have made some large improvements on the ImageNet challenge the last couple of years. So the green first bar is from 2011. That's classical machine learning algorithms, and we have quite large error. In 2012, that's the first introduction of deep learning, and we have a very large improvement in error rates, and it dropped quite much. And you can also see to the right in the diagram that the last year's entries actually is better than humans in recognizing the objects. There are some different types of learning problems we can work with in machine learning. The first and probably most common is the supervised learning problem. Algorithms are presented with example inputs and known outputs mapped to inputs. So in the example here we have the two inputs, 1 and 2, and an output. So 1 and 3 maps to 4, 2 and 1 maps to 3, and 3 and 5 maps to 8. And the learning task is to map the inputs to the outputs. So in this case we shall learn how to add two values together. And the output can consist of categories, and it's a classification task when we have a finite set of categories, for example the MNIST or the Cipher10 dataset. It could also be a continuous number, and in which case we call it a regression task. In unsupervised learning, the second type of learning problem, we don't know the actual outputs of the examples. We only know the inputs. And the algorithms are then left on their own to find patterns or structures in the input data. An example is to group news articles discussing similar topics together, a problem we call clustering. The third type is reinforcement learning. In reinforcement learning, systems learn from trial and error. The system executes an action in its environment and is given feedback on how well it worked out. If the action was a success, a positive reward is given. If the action was a failure, a negative reward or punishment is given. And over time, the system learns what actions are successful in its environment. And this is similar to how small children learn. An example could be that we can create a robot that learns how to best navigate in an environment, and the robot tests how to navigate over or around certain obstacles, and gradually it learns how to navigate in its environment. When we work with machine learning, there's two parts we do. We train a model, and we have to validate that the model actually has learned what we intended. So the actual machine learning algorithm is trained on a dataset in a training phase, and the dataset consists of a number of examples with known output. And this trained algorithm is called a model. And the model is used to classify new examples, and we can check how good the model is by calculating the accuracy. And the accuracy means the percentage of correctly classified examples. So in this case we have 150 examples, and 133 of them were correctly classified, and that leads to an accuracy of 95.33%. A problem is that if we use the same dataset for both training and testing, we don't know how good the model is on new and unknown examples. And this is what we often want to use our machine learning system for. We want it to classify new things it hasn't seen before. We can only know how good the model is at mapping known examples to output. And how good the model is on new and unknown examples is called its generalization ability. If we train too much on the dataset, the accuracy on the data increases, but we can get worse accuracy on unknown examples. And this is called overfitting. So as we see here, the error rate, the blue line, drops significantly on the training data and keeps dropping, but the error rate on unknown examples drops at first, but then it keeps going up again. And the optimal point to stop training is when the error rate on the unknown examples is as low as possible. And one way to improve the generalization ability and reduce overfitting is to use two datasets. The first and larger dataset is used to train the model, and it typically contains around 70 to 80% of the examples. And the rest is used to test the model performance. And we select the model candidate with the best performance on the test dataset. Another approach is to use cross-validation. In cross-validation, the dataset is divided into a number of buckets of roughly equal size, and common is to use 3, 5 or 10 buckets. If we use 10 buckets, the model is trained on 9 buckets and tested on the last bucket. And in the next iteration, another bucket is used for testing and the rest for training. And we repeat until all buckets have been used for testing and calculate an average accuracy. So the first iteration here, we have divided the dataset into 10 buckets, and the first bucket number 1 is used for testing and the rest for training. In the second iteration, bucket 2 is used for testing, the rest for training, and we continue until we have used all the 10 buckets for testing. So, should we use train test split or cross-validation? Cross-validation is a better measurement of a model's generalization ability, but it takes a longer time than train test split, because we need to train the model 10 times if we use 10 buckets. So we should use cross-validation if it doesn't take too long time. But if the data set is not that large, we can use cross-validation. If it's too large, use train test split. One quite common approach is to use cross-validation to fine-tune the model when training on a training dataset, because many models have different parameters we can fine-tune to make it work as good as possible on our data. And then we use the test dataset for final validation of the model performance. So we train the model, we validate the model, we have an accuracy score. Is the result good or bad? How good the accuracy is depends on how many possible categories the output can have. An accuracy of 50 to 60% on a binary classification problem, where we only have 2 categories, is hardly better than random chance. But the same accuracy can, however, be rather good if we have 25 possible categories. We can use what we usually call the ZeroR classifier as a baseline when comparing the results for different classifiers. ZeroR simply classifies all examples as the most frequent category in the dataset. And ZeroR has an accuracy of 33.3% on the iris dataset, since we have a balanced dataset with 3 categories. So a random guess would be correct in 33.33% of guesses. There's also some other performance metrics we can use when we work with machine learning problems. Accuracy is, as we already mentioned, is one of the most common performance metric for classification. It means the percentage correctly classified instances. So if we have 150 examples in the test dataset and 138 of them are correctly classified, we calculate the accuracy as 138 divided by 150, which equals 92%. And the problem here is that we only know the number of errors and the amount of errors, not what type of errors the model produces. The correct classifications can be of 2 types if we have a binary classification problem. The be true positives. We classify a correct example as correct, so a cat is classified as a cat. And we can have true negatives. We classify an incorrect example as incorrect, so a dog is classified as not being a cat. Then we have two types of errors. We have a false positives with type 1 errors. We classify an incorrect example as correct, so a dog is classified as a cat. And the other type of error is false negatives of type 2 error. Then we classify a correct example as incorrect. A cat is classified as a non-cat. And depending on the task, knowing if an error is of type 1 or 2 can be important. In, for example, an earthquake detection system, we don't want to start the alarm if there is no earthquake, because it can spread fear among people. So this is a type 1 error. It is usually better that we miss an early sign and most likely detect the earthquake a bit later. So we aim to minimize type 1 errors. Performance metrics that takes the type of errors into consideration are precision and recall. Precision is calculated for each category and measures how often the model is correct when classifying examples as belonging to the category. So all our examples that we think is cat, how often are they actually cats? And it's calculated as true positives divided by true positives plus false positives. Recall is also calculated for each category and measures the amount of examples that belong to the category that are correctly classified. So of all cat images, how many of these images are correctly classified? And it's calculated as true positives divided by true positives plus false negatives. And these two, precision and recall, can be combined into a single performance metric called F1 score, or sometimes just F score. And it's calculated as 2 divided by 1 divided by precision plus 1 divided by recall. Another important thing to look at when you work with machine learning problems is the confusion matrix. The confusion matrix shows the correct and incorrect classifications for each category. So in the example here we have two categories, A and B, and we have a matrix of classifications. If we take a look at the first row and the first column, we have 48, and it means that 48 of category A is correctly classified as category A. The second column, first row, means that 2 examples that should be A are misclassified as being B. In the second row, the second column, we have a number 46. It means that 46 of the examples belonging to category B are correctly classified as B. And the first column, second row, number 4, means that 4 examples that should be category B are misclassified as being A. So we want as high values as possible in the diagonal in the confusion matrix. So an example from the iris dataset, when we use 30 examples for testing, and we get an accuracy of 96.67%, only one misclassification, of iris setosa, the top row. We have 13 examples, all of them are correctly classified. The second row, iris versicolor, 8 examples were correctly classified as being iris versicolor, but 1 example was incorrectly classified as being an iris virginica. And in the third and last row, 8 examples were correctly classified as being iris virginica and no misclassifications. And when we can calculate the precision and recall and combine them into an F1 score for each category, and we can calculate an average value of the precision recall and F1 score for all categories. So the average F1 score for this model was 0.961. There are also some other things that we need to take into consideration when we select an algorithm for a problem. Training and classification time. Some model algorithms take a long time to learn, to train. Others can be fast but might not be complex enough for a certain type of problem. So we need to select an algorithm that is as fast as possible but is as complex so it can handle the actual task we are working on. We might also need to take into consideration the space consumption of a trained model. Some models have lots of parameters that we need to store, and in a mobile application, space consumption can be something we need to think about. Third is explainability. Can we actually understand what the model has learned? So, take an example. We go to a bank and we ask the bank guy if we can loan an amount of money. And the bank guy says, no, I can't give you that loan. And we ask why. Our bank guy says, I don't know, my machine learning system said no. And in this real world case, we typically want to understand why the machine learning system have given the answer is given. So we need to know why we cannot get that loan. And some algorithms, we can see what it has learned. We can typically check the model and understand what it actually has learned. And other algorithms, it's very difficult or impossible to understand what the model has learned. The fourth is the possibility of online learning. Can we continue training a model with new examples without having access to all data and retrain the system from scratch? Some models support this, some others don't. So that's all I had to say about data and learning. Thanks for watching.